Hello everybody, welcome back to part 6 of Combinatorics. This is going to be the last video, and I want to brush up on the Catalan numbers. So, in the end of part 4, I mentioned that looking at the ways you can arrange n sets of parentheses such that they are perfectly matched is equal to the nth Catalan number. And I want to sort of build upon that bijection to find another way we can express the nth Catalan number. So let's say, for example, we have the 5 by 5 grid again. So we're looking at C5. Then so let's say this is one of our paths. And I'm going to write basically some parentheses that correspond to this path. So here, basically each right move is an open parenthesis, and each up move is a close, because we can't have, they're basically the property of staying within the y equals x region corresponds to not being able to close more parentheses than you've opened. And so in that way we establish a bijection between this grid walk and the orderings of n sets of parentheses. So now let's look at this first set, or basically this first parenthesis and where it closes. And we can mark essentially that means that we will have hit this line at some point. So we're essentially breaking up the problem into two smaller grids. This is a 4 by 4 grid and a 1 by 1 grid. And in each sort of section of the grid walk, obviously, if we can't go above y equals x in the whole path, then we can't go above y equals x in the two smaller paths. So if we say that these two parentheses stay where they are, and then we look at how many ways we can order these two, then obviously this is C4, because ordering these is the same as ordering or doing a 4 by 4 Catalan grid walk, and obviously just doing one set of parentheses, just C1, which we know C1 is just 1, because obviously the only way to get from here to here is just right and then up. Obviously the only way to close one set of parentheses is open, close. So with that in mind, then as over all paths, over all possible C5 paths, suppose instead that we had a path, I'll change colors, we had a path that went, oops, sorry, that went something like this. So that the first time that we hit the line y equals x, besides from the origin, the first time that we hit it again is at the last point. Then we would obviously have an open set of parentheses. Then we would go 1, 2, I guess 1, 2, 3, and then close, open, close, close, close. So again, we're marking that these parentheses have to stay put. How many ways can we arrange these? Well, essentially, this is just C5, and we sort of have some notion that we have a C0 here. Essentially what I'm saying is that for each sort of possible path that will hit at some point, at this first point, we're creating, or basically establishing then that if we let that remain the same, how can we go from there, from that point on, to our target? And so what we see is that over all possible C5s, we'll get that, we basically get that C5 is equal to, hold on. I'm sorry. This should be C3. And, well, yeah, this is C1. This C3 and C1, and this should be C4. So we get that C5 is equal to, just ignore that, C4 times C0 plus C3 times C1 plus C2 times C2 plus C1 times C3 plus C0 times C4. Because we're basically doing, what we're doing here is for each case, we're looking at what point could a path possibly intersect at. And obviously there are 5 cases. And so each case corresponds to its own set of sort of parentheses where we have the first one stays constant and then we move around, we rearrange the ones, the two sets that we create, possibly creating an empty set here we have, which is denoted by the C0. So in addition to C1 equals 1, we have C0 equals 1. And then we can build on our definition here. So C2, for example, if we wanted to calculate C2, it would be C1 times C0 plus C0 times C1, which is 2. So what we've done here is we've established a recursive definition for Catalan numbers. Now, so recursion is just building upon what we have to get something new. Now, there are many common examples of recursion, and I know this isn't sort of what I should start out explaining recursion with, but it sort of gives you a good notion of the wide range of applications of recursion. I think the most common application of recursion would be the Fibonacci numbers, which is a sequence of numbers where each term is equal to the sum of the two terms behind it. Instead, we have that the nth Catalan number is equal to the product of Catalan numbers that add up to n minus 1. Their indices add up to n minus 1. In this case, we have 5 is equal to n, so each of these pairs, their indices add up to 4, because we basically fix one pair of parentheses, then that takes away, then we have n minus 1 more pairs, but we've created a division. It's sort of like stars and bars. We create a division between two sets. and we look at all the possible ways we can divide them. So we can divide them 4 on the left, 0 on the right, 3 on the left, 1 on the right, 2 on the left, 2 on the right, and so on and so forth to create a recursive definition for the Catalan numbers. So I might create a follow-up video. It won't necessarily be, because obviously this is the last part of the video, but a certain Amy problem this year, I found a solution using recursion that I thought was really nice. So I'm going to make a video on that, probably upload it tomorrow. Um, but basically many combinatorics problems can be tackled by taking essentially what we call a big problem, and splitting it up into smaller, identical small problems. And once we reach sort of a base case, which in our case is like 0 or 1, which we obviously know is just 1, or is something easy to compute, then we can just use our recursive definition to get the next form. Now, obviously, recursion is not nice specifically for Catalan numbers because we have a very simple and easy to compute explicit form. But for something like the Fibonacci numbers, where the explicit form is not so nice to compute, then recursion is a much more viable method. And in most cases, recursion is used for sort of an out in the wild problem that you would see on a competition instead of building an explicit form. And so I think that's it for my combinatorics videos. I might do more in the future if I brush up on sort of things like graph theory and generating functions, as I barely scratched the surface of what combinatorics is in this series. I just want to sort of give a broad notion of some of the techniques and how they can be used, which would be like bijection, combinations, bijections, stuff like that, recursion. So that's it for combinatorics. Thank you for watching, and I'll see you in my next videos. Bye.